Hey, Chris. Professor?
Yep. What's up?
Um, oh, it just went away, but it says stylus connected in the middle of the screen. I don't know if you see that too, but
Oh,
I
yeah.
I just couldn't read the third one, but now I can. It's all good.
Okay, great. Yeah, sometimes the Zoom screen share kind of lags a bit, but yeah, just let me know when that happens, and then I can clear it.
Okay, perfect. Thank you.
Mm-hmm. Okay, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing?
Pretty good, just tired. How are you doing?
Yeah, good. Yeah, tired. It's definitely time. It's when the semester really starts to get busy. So I know like midterms are coming up and everything like that. I know probably seniors, you guys are probably looking for jobs too. So it's a busy time. So definitely, make sure you get rest and make sure you're staying healthy because it's it's more important this time more than ever. Okay. So the plan for today is we're going to finish up our lecture notes on beam equations. And so the last thing that we have to cover is how to deal with distributed loading. Okay. And so distributed loading is basically, whenever you have a load that's distributed over a length. In this case, it's going to be a length of space. Okay. And so right now we can't really deal with these in finite elements because with finite elements, we kind of require our loads to be applied at the nodes. Okay. And so we're going to spend a big portion of today, saying how can we take a load that's distributed over space and then convert that into something that's distributed at just the nodes. Okay. And then after that, we're going to go ahead and move on. We'll see how much time we have left today. But then but after we finish the beam notes, the next thing is going over strong and weak forms. Okay. And so judging by, a lot of the feedback that I've gotten so far on the truss and beam equations, and just because of the fact that I know a lot of you guys have done these kinds of problems before in statics, I'm going to skip lecture note 05, where 05 had to do with frame equations, where frames are basically like trusses and beams combined. And so it's kind of like everything that we've been doing up to this point, but on steroids, just because you kind of, even problems that look relatively simple, you end up with like a 15 by 15, global stiffness matrix, which is, not fun to work with. So I'm going to skip that. And I'm going to move on to things that are a bit more interesting, which is kind of general, what I like to think about is like more general finite elements. Because up to this point, what we've been doing is what's called the direct stiffness method, which I think is good for just kind of getting used to the method, but it's not really what's applied in practice. So from here, once we move on to general finite elements, that will give you a much better idea of what's implemented inside software like ANSYS or Abacus or whatever finite element software that you have out there. Okay. Okay. And so another announcement I want to make is that the homework is due tonight. And so homework number 1 on the truss equations is due tonight at 11:59 p.m. And so right after this class, I have another lecture, but I'll try to still be available as much as I can because I know there have been a lot of questions on this homework. So if you have a question, it's not too late. The only time when it's too late will be after 11:59 p.m. tonight. So definitely send me your questions and I'll do my best to help you out as best I can. Yeah, it's long. Yeah, it's challenging. So it's I think generally what I've been seeing is that most of the mistakes that people are making are just arithmetic errors. And when you have to do so many calculations that are involved in this problem, like those are just bound to happen. So I think the challenge with these problems is just how tedious and how how detailed they can be. But just hang in there, and if you're not getting the answers that are in the homework, you can just send me your work and I can take a look as and give you as much help as I can. But yeah, problem 3 and problem 4 are pretty crazy. Yep, I am aware of that. Okay. And so I have your next homework prepped already too. So the homework, I won't post until after this homework's due, but that will be due next Friday. I think that's what I've set for that. Okay. And then that'll basically give us 2 good long homework assignments that we can have for the first midterm, which is going to take place I think in week 8 or week 7. Yeah. Oh wow, 17 pages. Yeah, that's a lot. Yeah. So I gave I gave a very similar homework. Your guys' homework was simplified a little bit, believe it or not, to my graduate students, and I had some of my graduate students for the finite elements for this particular unit turned in homework assignments that were like 20, 30 pages long. So it's it can definitely get up there. Yeah. Okay. So are there any questions I can answer either on that homework or anything that we covered last week that I can answer before we get started?
So you said something about sending your work or something if we're not getting the answer. Like, does that include like the MATLAB code we're using? Or
Yeah, anything I can help you with, just you can just send it over to me either on Discord or email. I'll help you guys out as much as I can up until the deadline, which is tonight. And so the only time I won't be available today is from 5:30 to 7, because and maybe until 7:30, because 5:30 to 7 I have another lecture that I do, and then 7 to 7:30 I have to eat dinner. But then from then I'll be available and try to answer your questions as many as I can. Mm-hmm.
Okay.
Yep. Okay. Any other questions? Okay, so let's go ahead and get rolling then. All right, and so last time we covered beam equations, which are kind of a different kind of flavor of finite element problems that we've been covering up to this point. Okay, and just to kind of remind you, the beam equations, they're different from the truss ones because they can support transverse displacements and rotations. Right? And so last time we went over the element stiffness matrices for a beam and how to do some beam problems and how to compute reaction forces and all that. Okay. So the last thing I wanted to cover in this unit on the direct stiffness method is distributed loading. Okay? Okay. And so I think probably the easiest way to visualize this is just with the picture. So let me draw kind of a simple beam like this. And so let's say that we have a simply supported beam, right? And by distributed loading, what I mean is, loading that looks something like this, right? So I'm sure you guys have seen distributed loading before, okay? So it's basically just a load that's distributed over a space, okay? And so this is different than what we've been dealing with up to this point. Because up to this point, we've only been dealing with cases where the loads are applied discretely at our nodes, okay? And that form is nice because we can just plug those straight into our finite element, loading vector, okay? Right. But when you have a distributed load like this, you're not able to do that, okay? And so in order to work with this, what we're going to need to do is we're going to need to take this distributed load and then convert it into a set of equivalent nodal loads. Okay? Okay. Because a distributed loading, usually, at least for this class, will be given to you in terms of a function. Okay? Right. So I'll call the loading function here w of x. Right. And so what we want to do is we want to convert this into a situation that looks like this. Right? And so instead of a load that's distributed over, what we're going to have instead are loads that are acting on the nodes of our beam. Okay. Okay. And this situation is what we would prefer because when you have all the loads applied at the nodes, then you can plug it straight into a finite element framework. Okay. And so the challenge is going to be, we can't just assign these loads, arbitrarily, right? And so up above, if we have w of x, we'll call this maybe p1, and we'll call this load here p2, okay? And so the challenge is going to be, how do we assign the value of p1 and the value of p2 such that these two guys are equivalent, okay? And so the key word here is equivalent, and it's kind of a loaded word in a sense because the word equivalent can mean a lot of different things. Okay, and so we'll talk about what I mean by equivalent and how do we actually compute P1 and P2. Because once we compute P1 and P2, then we can just use it straight up in a finite element framework, which we've been doing up to this point. Oh, I didn't even catch that. All right. Any questions on this? Okay. All right. So what do I mean by equivalent? Okay. So when I say equivalent, what I mean is the work that they do is equivalent. Okay. And so what I mean by that is, we're talking about work equivalence here. Okay. In other words, what we want to say is that the distributed load and the equivalent nodal loads, okay, these guys have to perform the same amount of work on our structure. Okay. And so how do we compute work from a load like this? Okay. And so we're going to have basically two formulas here. So let's first compute the work that's done by the distributed load. Okay. Okay. And so I'm going to call this W distributed or W dist. Okay. And so the way that we compute work, if you kind of think about just back from probably your first physics class, work is computed by multiplying a force over a distance. Okay. And so here for a distributed load, we have our our load function here, right? And then we're also going to have the deformation. Okay. And so this UY function here, this is our beam deformation function. Okay. And I'll show you the expression that we're going to put in for that, because actually, what we plug in for UY of X, that's going to be key to this kind of whole endeavor here. Okay. But since this load is distributed, what we're going to need to do is we're actually going to need to integrate this. Okay. And so when we integrate this product here of W of X times UY of X, and we integrate it from 0 to L, what we get is something in the units of work. Okay. Right. So just let me label this. So this Wx here, this is our load function. Okay. And so on one side, basically the work that's computed or the work that's performed by the distributed load, we have this formula right here. Okay. And so just to kind of summarize, this is the product of of our load function times the beam deformation integrated over the length of the beam. Okay. Okay. And so it's simply just force times distance, but applied with the distributed load. Okay. And so what we're going to do in order to establish this work equivalence, we're going to need to come up with a formula for the work performed by the nodal loads, and then set these two equals to each other. Okay. And so on the next page, I'll write out the equation for, what, how we actually compute this work by the nodal loads. Okay. All right. Any questions on any of this? Okay. All right. And so let me draw a figure here to kind of show or to illustrate the work done by the nodal loads. Okay. Right, so here's our beam. Okay. Normally we, before up to this point, we have a load that's distributed over this whole beam. But when we convert that to nodal loads, what we have is the following. Okay. And so we're going to have one force that's being applied on the left side. Okay, so we'll call this node 1, call this node 2. Okay. And so we're going to have F1y. Okay. We're also going to have F2y. Okay. And those are simply basically discrete loads that are being applied on the on the ends. Okay. And then in addition to that, because we have a beam, remember a beam also has rotational degrees of freedom. And so in addition to F1y and F2y, we're going to have a moment that's being applied on node 1, and also a moment that's being applied on node 2. Okay. And so we have basically four nodal forces that we can solve for here. Okay. And so to put this all together, remember the way that we compute work is force multiplied by deformation or displacement. Okay? And so we can do work nodal, okay, which is the work done by these nodal forces, is going to be equal to F1y, okay, which is the force that's being applied on node 1, multiplied by the deformation on that same node. Okay. And so the deformation, or the nodal deformation, this is typically what we solve for in our finite element solutions, will be U1y. Okay, so we're going to take that product. Then we're going to have the same thing for F2. Okay, so we have F2y, U2y. Okay. And then we have the work that's being done by the moments. Okay, so we're going to have M1 theta 1 plus M2 theta 2. Okay. All right. And so this formula right here gives us the work that's performed by our nodal loads. All right. And so in order to set up work equivalence, we're going to set this equation here on this page equal to this equation here on the previous page, and then work out, a lot of algebra. I'm going to give you guys fair warning now. It's going to be a lot of algebra here. Okay. In order to solve for these guys. Okay? And so our goal, remember, is to solve for these nodal loads right here. Okay. Right. And so, by the end of today, we'll do an example at the end. You'll see how we actually compute this. Right? It might seem like a daunting task because we have four unknowns here and technically only one equation. But what you'll see is that from this one equivalence, we'll be able to set up, 4 equations for it. Okay. Okay. All right. And so what we want to do is we want to set work distributed, which is on the previous page, equal to work nodal. Okay. Right. And then once we do that, we'll be able to perform the integration and then work out what these nodal loads are. Okay. All right. So there's only one problem here. So actually, this expression here for W nodal, this is fine. So we're going to keep this as is. But if you look back to our equation for W distributed, we have 2 functions in here, right? And so we have W of x, which is our load function, and we also have Uy of x, okay? Right. And so before we actually, start to work this out and start integrating, we need to plug in expressions for W of x and Uy of x, okay? All right, so the nice thing about this is that W of x, which is your load function, this is, always going to be given to you, right? You can kind of revert the problem where you can solve for this, but just for this class, you can kind of assume that W of x should always be given to you. Okay. Uy of x is a different story. So Uy of x, remember the way that we interpret this is how the deformation of the beam varies, in space. Okay. And so in order to get Uy of x, what we need to do is we need to assume a function. Okay. And then from that assumed function, we can go ahead and just plug that in and solve for it. Okay. And so what you'll see on the next page here is that, you know, assuming functions is actually a core part to a lot of finite elements. And so you don't really see that in the direct stiffness method up until this point. And so if you kind of think back to our ANSYS activity 1, do you remember when we were doing the mesh, there's a part of the activity where we had to specify whether we want our elements to either be linear or quadratic, okay? And so you'll get a little bit of a glimpse of what that is right here. And then you know, we're going to expand on it a lot more, you know, in the coming weeks when we do general finite elements. But at least for here, you'll be able to see what that actually means. Okay. Any questions on this? Okay. All right. And so let's go ahead and start, you know, talking about how we're going to assume u of y. Right, so just to start us off, let me give u of uy here you know, a formal definition. Okay? And so uy of x here, what this is this tracks the transverse displacement on the beam as a function of x. Okay, and so if you have a beam that looks like this, okay, and let's say that the x direction is this way, okay, then a uy of x would be something that, you know, say that we have a distributed load on this, might look something like this. Okay, and so uy of x here basically tracks, you know, how the beam deforms as a function of space. Okay, and the way that we usually obtain this is we solve the beam equation for it. Okay, and so just to kind of remind you, the beam equation, or at least the one that we are working with, looks something like this. Okay, and so it's a fourth order differential equation. So we have EI times d to the fourth UY all over dx to the fourth. Okay. And so if you basically solve this ODE right here, if you solve this differential equation, you'll obtain an expression for uy. And of course, this is going to be subjected to boundary conditions in order to solve for all the constants. Okay. And so that's what you would do normally to solve for u of y. But in this class, you know, we're not really interested in solving these ODEs, right? Because we're interested in doing finite elements. And so what we're going to do instead of solving this, we're gonna half solve it. And so you know, what we're going to do is we're going to assume a form of the solution that satisfies this equation. Okay. Satisfies. I always have issues whenever I go to that bottom portion of my iPad. Another one of my classes, you know, and I know there's some people in here in that class too, is that they make memes of my handwriting after every lecture. So every lecture, what happens is I go to the Discord channel, I see more memes of, you know, my handwriting there. Okay. And so, you know, at this point, you know, there's actually a lot of freedom, you know, through which you can assume a function, right? Because there's, in the world of math, there's so many different functions out there, right? So you can have a polynomial, you can have like an exponential, you can have a sinusoid, you can have every kind of combination in the sun, okay? But for finite elements, typically the kinds of functions that we like just because they're simple and they take derivatives really easily, is we really like polynomial functions. Okay, and so for this particular case, let's assume a cubic polynomial. Okay, and so the most generic cubic polynomial looks like this. Right. And so, you know, a generic cubic polynomial has to have x cubed, because that's where it gets the name cubic, but then it also has every power of x before this, and also a constant term. Okay. And so, you know, when we assume this solution, you know, and we plug this back in here, you can see that it satisfies this equation, because if we take 4 derivatives of this guy, then we can see that everything goes away and we just end up with 0. Okay. And so this is, you know, this is kind of a sneak preview of where we're going with general finite elements, where, you know, you're going to have to assume a solution, plug it back into your governing equation that satisfies it, and then, you know, use that to solve for all the unknowns. Okay. Because right now, all of these you know, coefficients that I've circled here, they're unknown up to this point, and so we don't know what their values are. Okay? And so usually the process of, you know, plugging this back in and applying boundary conditions to solve for this is usually a very lengthy process. And actually for this beam, it's actually very, very lengthy. So, you know, I'm going to skip most of the work. I'll show you how to set up the problem, and you can kind of work out the math if you're interested. But, you know, we're not going to kind of work through that. So from here, I'm basically going to show you kind of the end result for UI. Okay. Okay. Any questions on this? Okay. Okay. And so kind of, you know, it's at this point, it's kind of, you know, good to kind of step back and kind of remind ourselves why we're going through this, right? And so, you know, the reason we're going through this is we want an expression for UI right here that we can plug back into our, you know, principle of equivalent work, okay? Because in order to basically plug in for this equivalence right here, we need a function for UI that we can just plug in, okay? And ideally, what we would want from UI, we don't just want any UI of x. In fact, what we want is we want UI of x to have our nodal quantities to it, okay? And in particular, you know, we want them to have our nodal deformations in this expression. And remember, our nodal deformations here, we have 4 of them. And so we have U1y, U2y, theta 1, and theta 2, okay? And so these are the transverse displacements at the 2 nodes, 1 and 2, and also the rotations at nodes 1 and 2, okay? And so in order to make sure that we get these inside UI, we're going to apply the following conditions on UI. And so basically we're going to require that if we plug in x is equal to 0 into UI, then what we get is the first nodal displacement, okay? And so if we evaluate UI at x is equal to 0, we should get UI1, okay? And then if we evaluate the function x is equal to L, remember this is the right side of the beam. And so what we should get from this is U2y, okay? Which is the nodal displacement on the right side of the beam, okay? And so that's, you know, that's how we get our 2 nodal displacements. And let's see how we get the nodal rotations, okay? And so the first nodal rotation is going to be obtained by taking the derivative of uy with respect to x and setting that equal to theta 1. Okay. And then the same thing that we can do on the right side of the beam, we can take the derivative of uy with respect to x, set x is equal to L, and that will give us theta 2. Okay. Right. And so what we have right here, if you kind of remember from 308 or your previous math classes, is we have 4 boundary conditions through which we can solve for these 4 constants. Okay, so we have four a values, a0, a1, a2, and a3, and then we have 4 conditions here through which we can solve for their values. Right. And so, I'm going to skip that step of actually solving through it because, in the end for this, it's not that important. Because I want to focus more on how we can actually compute our nodal loads, and so I'm going to go ahead and skip to the end for this. Okay. And so if you apply these conditions to our assumed form for uy, then what we get is the following. All right. And so be ready because it's a little bit of a monster here. Right? Right, so our first term in uy of x is going to be 2 over L cubed times u1y minus u2y plus 1 over L squared theta 1 plus theta 2, and all that multiplied by x cubed. Okay, and so that monstrosity right there, that was just one of the coefficients, right? So this was a3 right here. Now we have 2 more coefficients to find, right? And so now let's write out a2. And so a2 is going to be minus 3 over L squared times u1y minus u2y minus 1 over L times 2 theta 1 plus theta 2 x squared. Okay. And so that's the second coefficient for, for the x squared term. Okay. And then finally, we're going to have theta 1 times x. Okay. So thankfully, that's a short term. And then the last term is also very short, too. This would be u1y. Right. And so it's lengthy. So it's very long. And and this isn't even the work that we have to do yet. So what we're going to do in order to convert our distributed load to nodal loads is we're going to plug this into our integral, multiply this by w of x, and then integrate the whole thing. So it's going to be a lot of math, but I'm going to do an example with you guys, and we're going to go pretty slow through it, just so you get every single step. Yeah, it's not fun. So that's I'm actually kind of glad that we're after this we're going to move on to general finite elements, because this direct stiffness stuff it's good to, I think it's good to start to kind of introduce the idea of finite elements, but the math and the problems are definitely not fun. Okay, but I'll tell you this though. So when we're performing our integral, everything that I have here in square brackets, this guy, this guy, and this guy, and this guy, all of these you can consider constants, right? So actually the only thing that we're going to be integrating are just simple powers of x, right? So we're just going to be integrating basically x cubed, x squared, x, and a constant, right? And so it's going to be a lot of writing. And so, I'm not going to deny that there's a lot of, writing to be done here, but the integration itself is fairly simple because we're just integrating polynomials, which, I think we've, a lot of us have kind of done to death at this point. Okay. All right. Any questions on any of this? Okay. All right. So now we have everything that we need to actually perform our work equivalence expression. Okay, because remember, where we started was this right here. Right? Right. We wanted to form this equivalence here between W distributed and W discrete. Okay, where W distributed is given by this expression, and so we have our distributed mode W of x times Uy of x, okay, dx is equal to f1y u1y plus f2y u2y plus m1 theta 1 plus m2 theta 2. Okay. And so in this example problem, what you'll see is that I'm going to plug in for w of x, which is going to be given to you in the problem, and then we're going to plug in for uy of x, which is what we just had on the previous page, perform the integral, and then kind of work out the math from there. Okay. And so this entire right side of the equation here, we're going to leave that alone, and so you can kind of ignore that, while you're performing the integral, and then once you're done with the integral, you can kind of bring it back to here. Okay. All right, so let's do an example here. Okay. Right, and I'll at least give you this solace that this example that we're going to do right now is as complicated as I would expect you guys to do. So the homework, the distributed loading in the next homework assignment is going to be simpler than this. Okay, and so let's consider a beam that's subjected to a loading that ramps up in space. Okay, and so it looks like this. Yeah, everything's relative, right? So it won't be worse than this. I would say for these calculations. Right, and just with the nature of these distributed mode calculations, since they are very lengthy, I'll tell you right now that I would never ask you to do something like this on an exam, just because it just takes way too long. So at least you have that to hopefully make you feel a little bit better. All right, and so let's say that our loading function looks something like this. And so, we base on the left-hand side of the beam, we have basically no load. And on the right side of the beam, it really ramps up from there. Okay, so we'll call this node number 1, call this node number 2. Okay. The length of the beam here is going to be 1 meter, so we'll keep it simple. Okay. And the function for this loading, which is given to you, is going to be 5,000 x newtons per meter. Okay. Right. And so now we see basically what our load function looks like. Okay. And so what we're going to do is now that we have w of x, we're going to plug that in here. We're going to plug in uy from the previous page into here, okay? And then perform the integral and then set it equal to the right-hand side. Okay. And so if we plug in for all of those guys, we end up with the following expression. And so our w of x here is going to be 5,000x. Okay. And then we're going to plug in our expression for uy. Okay. And so uy, as we plug in from the previous page, is going to be 2 over L cubed. Right, times u1y minus u2y plus 1 over L squared, theta 1 plus theta 2, okay, x cubed, okay, plus minus 3 over L squared, u1y minus u2y, right, minus 1 over L times 2 theta 1 plus theta 2, okay, and this is x squared plus theta 1x plus u1y, okay? And all this is integrated dx, all right? Okay, and so the next part of this problem is we're going to evaluate this kind of monstrosity of an integral right here, okay? But I'll give you a trick, and so this will kind of help you save some sanity, okay? Because remember what I said on the previous page, that all of these guys in the square brackets, all of these guys are simply just constants, right? And so when we perform integrals, we don't really care about the constants. We just kind of, just kind of move them from line to line. And so to kind of save yourself some sanity of having to write this out, and save me some sanity too, then let's just replace these with just arbitrary constants for now. Okay? And then at the end, we'll plug back in for them because we're going to need them to solve for the actual nodal nodes. But when we're actually performing the integral, we don't need them yet. Okay. Okay.
Just wanted to double check. In your notes on that same integral, your last term, the u1y, you have an x at the end of it in your notes.
Oh, there should not be. So the u1y should just be a constant on that one. Did I do that on the previous page?
I don't believe so.
Okay. Yeah, that u1y, that last one there should just be a constant. So there's no x on that one. Yeah.
Okay, cool.
Mm-hmm. Okay. And so let me go ahead and rewrite this integral with those constants there, just to kind of save us some sanity. Okay. All right. And so the integral that we're going to perform is going to be from 0 to L, and we can go ahead and plug in for L at this point, because we know for this particular problem, L is 1. Okay. So we're going to perform an integral from 0 to 1 of 5,000x, and that's our w of x function. Okay. And then to that, we're going to multiply by a3x cubed plus a2x squared plus a1x plus a0 dx. Okay. And you can see this is a lot more manageable than before. Okay. And so let's go ahead and distribute this 5,000x through. Okay. Or actually, I'm going to take this 5,000 and pull it out of the integral because it's just a constant. Okay. Okay. And so if we distribute that x through, then we just have the following. All right. And so now let's perform the integration. And so performing the integration, we have a3 x to the 5th divided by 5 plus a2 x to the 4th divided by 4 plus a1 x cubed divided by 3 plus a0 x squared divided by 2, okay? Evaluated from 0 to 1, okay? Right. And so now let's evaluate the integration bounds here. And so we get 5,000, okay, a3. And so since we're evaluating this between 1 and 0, this first term here is just going to be 1/5 plus a2 times 1/4 plus a1 times 1/3 plus a0 times 1/2. Okay. Okay. And so, up to this point, this is just kind of simple, integration of a polynomial, right? And so now that we have this expression here, so we've performed the integral, let's plug back in for all of our a coefficients. All right, so this is where things will get fun or not. Okay. Okay. And so let's do A3 first. So for A3, we're going to have a 1/5 out in front. Okay. And A3, if we go back to the previous page, had this coefficient here, right? So we had 2 over L cubed times U1y minus U2y, okay? Plus 1 over L squared, theta 1 plus theta 2, okay? And so that was our A3 term. Next, we're going to plug in our A2 term, okay? And so our A2 term is going to be 1/4 times minus 3 over L squared U1y minus U2y, okay, minus a 1 over L times 2 theta 1 plus theta 2, right, plus A1 divided by 3, and so we're going to have 1/3. A1 in this case is just going to be theta 1, okay, plus a 1/2 times A0, where A0 here was just U1y. Okay. Right. And so we end up with this expression here. Okay. Right. So I know it's a lot, so I'll give people a second to write it down. And so, you know, while people are kind of catching up, are there any questions on this? Okay. Okay. And so now that we have the equation in this state, what we're going to do is we're going to, you know, you'll notice that we have a lot of U1y's and U2y's that are floating around and theta 1s and theta 2s. Okay. And so what we're going to do at this point is we're going to group like terms and such that we get 4 terms, you know, 1 for U1y, 1 for U2y, 1 for theta 1, and 1 for theta 2. Okay. And so next step is group like terms. And thankfully, you know, after we group the like terms, then we'll basically be done from here. Okay. Right. Because then what you'll see is that, you know, our equation is going to be in the same form as the right-hand side, and we can just read off, you know, our nodal forces just straight from there. Okay. Okay. All right, everyone good for me to turn the page? Okay. Okay. All right. So let's keep going. Oh, one more thing. So we since we you know, we still have some L's here. So let's go ahead and plug in L is equal to 1, just to kind of simplify our math. Okay. Okay. And so let's go ahead and start distributing this this guy. Okay. And so let me, just to make things clear, let me kind of repeat what was on the last page, but we set L is equal to 1. Okay. And so we have 5,000 times 2. Normally we have 2 over L cubed, but L cubed here is just, you know, 1. Okay. I forgot our 1/5. Okay. And so we have 1/5 times 2 times U1y minus U2y. Okay. Plus theta 1 plus theta 2. Okay. We had a 1 over L squared there because since L is equal to 1, we can just change that to just 1 like that. Okay. And this is going to be plus 1/4 times, normally here we have minus 3 over L squared. We'll just have minus 3 times U1y minus U2y. Okay. And then we have minus 1 over L, but L here is just 1. And so we're going to have 2 theta 1 plus theta 2. Okay. And then we have theta 1 divided by 3 plus u1y divided by 2. Okay. All right. And so this first step, what I'm going to do is I'm going to take these factors out in front and distribute them through. Okay. And I'm going to take these factors here and distribute them through as well. Right. Just so that we have everything that's kind of separate and no more parentheses. Because once we have everything without parentheses, it's easy to kind of look at that expression and find all the ones that are same. All right, so we still have our 5,000, so we can't forget that guy. Okay, and the first thing we're going to have is a 2 over 5 u1y, okay, minus 2 over 5 u2y. Right? And so that's the result of performing that first distribution there. Right? Then we're going to have theta 1 over 5 plus theta 2 over 5. And so all I did here was I just distributed that first term, everything divided by 5. Okay. Then we're going to have everything on this guy. Right? And so next we're going to have a minus 3 over 4 u1y, okay, plus 3 over 4 u2y. Okay. Then we have a minus 1/2 theta 1, and then we're going to have a minus 1/4 theta 2. Okay, and so that's the result of distributing that 1/4 through that second parentheses term. Okay. Okay, then we have theta 1 divided by 3 plus u1y divided by 2. Okay. And so now at this point, now that we have everything kind of distributed through, we can just kind of group all the terms, group all the like terms together, okay? Okay. And so next step, we're going to bring our 5,000 down. And then now I'm going to start grouping the terms. So let's start with the u1y's. Okay. So let me go ahead and circle all of those. Okay. So first we have a 2/5. Then we have a minus 3/4. And then we have a plus 1/2 here, okay? And so we have 2/5 minus 3/4 plus 1/2, okay? And all this is multiplied by u1y, okay? Next, let's do the u2y terms. And so for u2y, we have a minus 2/5 here and a plus 3/4 there. Okay. Okay. Next, let's do the theta 1's. So we have theta 1 over 5, minus 1/2 theta 1, and then a theta 1 over 3. Okay. So we have a 1/5 minus 1/2 plus 1/3 theta 1. Okay. And then finally, we have our theta 2 terms where we just have 2 of them. So we have a positive 1/5 and a minus 1/4 here. Okay. Okay. And so we have 1/5 and then minus 1/4 theta 2. Okay. All right. All right. And then we're going to, from here, we're just going to simply add up all these guys together. Okay. So we still have 5,000 out in front. And if we add up all these fractions, and so you can just do this in a calculator, we're going to have 3 over 20 u1y, okay, plus 7 over 20 u2y, okay, plus 1 over 30 theta 1, okay, and then minus, I have a typo in my notes, so let me just do it real quick, minus 1 over 20 theta 2. Okay. Right. Everyone still with me so far? I'll give you guys a second to write this down. So while we're kind of pausing here, are there any questions on any of this? Okay. I'll give you guys a couple more minutes to write this down. Yeah, it's a lot of arithmetic, so but this is probably the only time that we'll see kind of something this intense, at least in terms of integrals and combining like terms and all that stuff. And so just kind of naturally with the direct stiffness method, you get a lot of things like this. So you've kind of already seen with the truss problems, there's just a lot of matrices and a lot of really tiny calculations, by themselves, they're not that hard. It's just a lot of adding and plugging in, but because there's just so many calculations, it's pretty easy to kind of make mistakes. But just by the nature of the finite element method, and and this is true for any method that's actually designed more to work in a computer, it just ends up being a lot of repetitive calculations. And so if you take kind of a similar class to this, like another class I'm teaching this semester is 417. A lot of it's very similar to this, where it's just a lot of really, simple calculations, but it's really repetitive, really tedious. Because normally, you would have a computer do this, but but because we're taking, we're learning the class, understanding the theory behind it is a big part of taking the class. Okay, and so now that we're done with that, we're basically done. And so the only thing left to do here is just to distribute this through. 417 is computational heat transfer. And so it's kind of, whereas finite elements, we focus more on, structures, just because that's kind of what a lot of finite elements is used for. 417 does more, it's kind of, it's more about computational methods to solve heat transfer and fluid mechanics problems. Okay, so let's go ahead and perform the last step. So let's distribute this through. Okay. And so if we multiply 5,000 through, we end up with the following expressions here. Okay. And so we end up with 750 U1Y plus 1750 U2Y, okay, plus 500 over 3 theta 1 minus let's see, 5,000 divided by 20 minus 250 theta 2. Okay. And then, believe it or not, at this point that we're done, right? Because if you remember, where we started was, we had this kind of really nasty integral on one side of the equation, and on the other side of the equation, we had our expression with our nodal loads, right? And so on the other side of the equation, we had this, right? So we had F1y, U1y plus F2y, U2y plus M1 theta 1 plus M2 theta 2, okay? Right. And then what you can see here is that because their coefficients are the same, we can make these equivalences here, right? Okay. And so in the end, now we have expressions for F1y, F2y, M1, and M2, okay? Right. And so we basically have F1y is equal to 750 newtons. Okay. F2y is equal to 1750 newtons. Okay. M1 is equal to 500 over 3 newtons meters. Okay. And M2 in this case is going to be a minus 250 Newton meters. Okay. Okay. And so if we bring this back to our beam, right? now instead of that distributed load, where remember we had that ramp function, what we have now are the equivalent loads that are at the nodes, okay? And so we have a F1y, F2y, okay? We have an M1, and we also have an M2. Right, so all of these guys are in replacement of that distributed load. And so now that we have the loads in nodal form like this, now you can do a finite element problem, and you can do all the fun stuff with the element stiffness matrices and the assembly and all that stuff. So, you did all this work, and now you get to do kind of more work on top of it. So yeah, distributed loads are not the easiest things to deal with. So that's why I kind of mentioned earlier that on an exam, I wouldn't ask you to do I wouldn't ask you to do something like this, because you would do the whole thing with the distributed load, and then you'd have to do the finite element problem on top of that. So so this is something something that's good. And actually, if I can admit something, before I kind of developed these notes, I actually didn't know this myself either. So this is kind of just something good to have in your toolbox. Just so you can kind of perform some calculations out there professionally, right? But in terms of doing calculations for an exam or something that I would expect you to do something like that, I wouldn't expect you to do this. But I will say that there is a problem on the next homework with distributed loading, but the function is simpler. So the function is just going to be a constant function, and so you can you can look forward to that. Okay. All right. Any final questions on distributed loading before we move on to strong and weak forms? Okay. All right, and so that kind of closes the chapter on the direct stiffness method. So, I know our exam still isn't for a couple more weeks, but this is kind of the stopping point for our first exam. And so, because I'm skipping the frame stuff, that kind of puts us at a weird stopping point. And so, what we're going to start from here on out is general finite elements, but that stuff's not going to be on the first exam. So this is kind of the stopping point. And so for the first exam, what you have to worry about is just course introduction, trusses, and beams. Okay, and then all the general finite element stuff, we'll worry about that for the second exam. Okay, and so now let's go ahead and launch into our next unit here, which is on what I call general finite elements.
Professor?
Yep.
Are we gonna have to use ANSYS at all on the first exam or no?
No. So the exams, the way I kind of structure this class is the exams I focus, just purely on the theory, just because I don't, especially in a virtual setting like this, because I know everyone's computers perform differently. So I don't want like lag and ANSYS or ANSYS crashing to be like a factor on the exams. And so
Okay.
For exams, I just focus on the theory, and the ANSYS activities and the final project. That's everything for ANSYS that we're going to do.
Okay.
Yeah.
Thank you.
Okay. And so let's talk general finite elements, right? And so up to this point in the class, we've been working with the method called the direct stiffness method, right? And so generally the way the direct stiffness method works is that, we have very specific types of structural elements. And so we looked at springs, and we looked at trusses, and we looked at beams, right? And then for those elements, I kind of just gave you, or, we kind of pseudo-derived their element stiffness matrix, right? And so from that, we're able to solve, fairly complex structural problems, right? And the nice thing about finite elements, or the direct stiffness method, is that you can come up with a very, very complicated structure, right? So you can even come up with like a suspension bridge, right? We might have like 30, 40 elements, and maybe a few dozen nodes, and you can solve that problem, right? And by hand, no less, right? And so it would probably take you a long time, but it's something that you could actually do, right? And so, the thing with the direct stiffness method, it works great for structural problems. But, even though that direct stiffness method, I think is really great for, kind of illustrating or kind of as a first exposure to what finite elements are. Right? Yes, so we're officially done with direct stiffness method as of this point. Yeah. And so even though the direct stiffness method is great for kind of, introducing finite elements and, introducing the idea of an element stiffness matrix, and assembly and applying boundary conditions, kind of like what I mentioned before, it's not used that much in practice. And in fact, it's kind of selling finite elements short, right? Because finite elements is a lot more than just a tool for solving structural problems, okay? And so kind of the formal definition that you'll see for finite elements is something more like this. Right? And so a more general definition for finite elements is that it can actually tackle any differential equation that you can come up with. Right? And so finite elements basically gives you a way to solve, these differential equations. Actually, I won't say any, so I'll say almost any. It's hard to talk in absolutes without a counterexample coming in just kind of smacking you in the face, right? So I'll say it can solve almost any differential equation. Okay. Right, and it gives you a way. Oh, question. Yes. Yeah, so the cutoff, the cutoff for the first exam was 5 minutes ago. So after everything before 5 minutes ago will be on the first exam, and everything after that will not be on the first exam. Okay, and so if you need proof of the statement right here, where finite elements gives you a way to solve any differential equation, just open up ANSYS, right? And so if you remember when we first opened up ANSYS Workbench, on that left side of the screen right there, we saw a bunch of different, types of equations that we can solve, right? And so we focused on just one last time, which was just static structural. But if you read some of the other entries in that list, we have things like steady state thermal, we have fluid flow, we have transient thermal, we have transient structures, we have, vibration analysis, we have, modal analysis. And so, the possibilities with finite elements is really almost endless, right? And so if you can think of a differential equation to solve, finite elements will be able to solve that for you. Okay. Okay. Because the thing is with engineering physics in general, so all think of all the classes you've taken up to this point in mechanical engineering, or if you're coming from a different department for other engineering, most of the time the governing equation for that type of system is a differential equation. A lot of times it's a partial differential equation, which is sometimes literally impossible to solve by hand, like Navier-Stokes, but it's a differential equation. Okay. And so what finite elements allows you to do is it allows you to basically solve those differential equations on a mesh. Okay. And so that's kind of the power, and that's kind of why finite elements kind of really has risen so strongly in engineering analytics, is because a lot of the systems that we're interested in terms of engineering, they're governed by differential equations, right? And normally it's too hard to solve those differential equations by hand. And so finite elements kind of rose as a method to actually solve those guys, on complex geometries. Okay. All right. And so let's define some things before we actually get started. Okay. And so the types, and so the formal name for an equation that can be solved with finite elements is actually not differential equation, even though a differential equation is involved. But the type of problem that we usually say is we usually call them a boundary value problem. And sometimes the boundary value problem is abbreviated by BVP. Okay. Right. And so there's a few aspects to a boundary value problem, and these are kind of the prerequisites that you need to run any kind of finite element simulation. Okay. And so what you'll see from ANSYS that you have to supply a lot of these things into ANSYS as well. Either you have to manually provide a file that represents this, or you have to manually specify that setting within ANSYS. Right. And so the first thing that you need for a boundary value problem is you need your domain. Okay. or another word for your domain is simply your geometry. Okay. And so first you need to define, what geometry or where you want to solve your differential equations. Okay. And so, of course, this is going to depend on what type of problem that you're solving. Okay. But just for the purposes of this class, I'm going to draw my usual kind of potato/amorphous blob right here. Okay. And then we'll say this is our geometry or our domain for our boundary value problem. Okay. And so practically, the way that you specify this is you usually supply some kind of CAD file. Okay. And so in our ANSYS activity that we're going to do next Thursday, I'll show you how this works. So for the ANSYS activity next Thursday, I'm going to give you a CAD file, and then you're going to load that into ANSYS and perform a finite element simulation on it. No, it's a ditto. Yeah, that's another name for it. Okay. Okay. And so that's the first aspect of a boundary value problem. And so before you kind of start any kind of finite element problem, you need to define your domain. Okay. And so if you think about the direct stiffness method, the domain or the geometry was kind of given to you as an assembly, usually as an assembly of springs, trusses, and beams. Okay. And so for general finite elements, it's no different, except now we can be a lot more general and a lot more arbitrary for what we specify for the domain. So we're not just limited to beams and trusses anymore. So now we can do basically anything that we want. Okay. All right, any questions on this so far? Okay. All right, and so the next aspect of a boundary value problem is going to be its governing equations. Okay. Specifically, its governing differential equations. Okay. And what this equation does is it basically describes the physics of your situation. Okay. And so depending on what type of physics that you expect or what kind of situation that you have, you're going to have different governing equations, right? And so this step, if you kind of relate this to what we did in ANSYS, this is kind of one of the very first things that we do in ANSYS. So we have to select what type of analysis that we want. And so, the one that will focus most on this class is the static structural, which is, saying that we want to solve a structural problem. Okay. And so structural problems have their own, differential equation that that governs their behavior. Okay. And so implicitly what you're doing in ANSYS when you're selecting the type of physics is you're telling ANSYS, which differential equation that you want it to solve. Okay. And so, but if you want to solve some different kinds of physics, or even, more complicated, you want to solve coupled physics, so you want to solve kind of two things at once, you're going to have to define different types of equations for that. Okay. All right. And then the last thing that you need, okay. And so this is just kind of general boundary value problems. And so, even though all these are prerequisites to finite elements, I'm not going to talk about things like meshing and that stuff like that, because that's unique to just finite elements. But for any boundary value problems, you need at least these two things. And then the last thing that you need is also the boundary conditions. Okay. And the reason you need boundary conditions is that you need a way to specify, what's going to happen on the outsides of your domain. Okay. And so remember, this is something that we specified in ANSYS too. So a big part of ANSYS was specifying the loads and constraints, right? And so that's essentially assigning boundary conditions. Okay, and so we're out of time for today. So what we're going to pick this up again on Thursday. And on Thursday, you know, we'll see how we can apply this theory of boundary value problems to 1D differential equations. Okay, and so we're going to do, hopefully remind you of some of your differential equations classes. So either 308, or I know there's a class in the math department too. You know, and we'll see, you know, how we can actually apply finite elements to just general differential equations like that. Okay. All right. So thanks everyone for tuning in today. That's all we got time for. And so, you know, I can stick around for about 5 minutes, but I do have another class after this, so I can't stick around too long. And so if you're having problems with the homework, you know, that's due tonight, definitely send me an email, send me a Discord, and I'll help you out as best I can. Right. All right. So have a great day, everyone, and I'll see you everyone on Thursday.
Thank you. Have a good rest of your day.
Thank you, Professor.
Thanks, guys.
Thank you.
Arjun, did you have any more questions? Okay. So if not, I'm going to go ahead and close the call. So see you on Thursday.
See you. Sorry about that.
Oh, no problem. All right. See you Thursday.